Happy to be here. I'm Jody. I'm a PhD student working in South Pole Telescope. Today I will give an overview of that, and then Marius will talk about Bayesian methods. So the SPT is a 10-meter telescope at the Amundsen Scott South Pole Station. So due to the high altitude and low water vapor and a stable atmosphere, we have a very low atmospheric noise. And also we can make arc-minute resolution maps thanks to the 10-meter aperture. There has been 3 generations of camera installed on the SPT. The latter 2 are polarization sensitive. And for SPT 3G, the 3rd generation, we have 16,000 bolometers and 3 frequency bands, 95, 150, and 220 gigahertz. So actually, that's a lot of time-ordered data. We'll talk about that in a sec. The main SPT survey, SPT 3G survey, will cover a 1,500 square degree of sky, shown in the orange contours, and it overlaps with the BICEP experiments. Due to the low noise at the South Pole, we take advantage of that, and we drill really deep on this field over many years. And so you can look at the projected numbers on the right. We expect to reach 2 to 3 micro-K arc-minute depth at 150 gigahertz. That's over many austral winters when it's dark most of the year. But there's the austral summer when the sun actually rises, it will contaminate this field. So that's when we move to observe this other red patch. We call it the extended field. And some of this extended field is on this side, but if you look at the second picture, we also observe some of the field on the opposite side of the celestial sphere. This has an additional 2,600 square degrees, so this will be useful for lambda CDM constraints. So in addition to doing lambda CDM power spectrum analyses, we can also measure the CMB lensing potential. We can use it for delensing, and can use it for joint analysis with BICEP Keck, as you've heard from their talk earlier today. The lensing template is also a tracer of large-scale structure, so it's helpful to cross-correlate this with the dark energy survey. And then we can study point sources, galaxy clusters, transients, and all kinds of stuff. So the main data analysis challenges are the usual ones you would encounter, so CPU and storage. So we need a lot of CPU time, mostly for mock observing. Currently, we use the Open Science Grid for that. Also, as I mentioned, we have a lot of data. So we have 16,000 bolometers, and the uncompressed raw data of the time stream is about 1 terabytes per day. And this whole experiment will go on for several years. So we actually need petabytes of storage space. For example, this is what a example time order data looks like. And I also plot the RA. So we scan back and forth. The time order data will have some large scale drifts due to the atmosphere. So here I'll describe the usual method, which is the pseudo-CL method following the master algorithm. But after me, you will hear from Marius about the Bayesian methods. So in the usual method, we will filter these time streams. For instance, here we subtract the legendary polynomial to remove the large scale structures, the large scale noise. We also notch filter if possible, if needed. We also apply a common mode filter that subtracts the signal that is common to a specified group of detectors. This can help decrease noise. And we can apply high pass and low pass filters. So after all these filters we've done to the time stream, we will need to perform mock observations as well on simulated sky maps and perform all the same filters in order to obtain the filter transfer function. So that's what we will need in order to convert back from the pseudo CLs back to a true unbiased CL. Yeah, and so after, okay. Oh, but before that though, in the map space, we also have a couple of systematics. So for instance, we have a scan synchronous systematic. For instance, this is a temperature map in SPT pole. We have found there's a, say, looks like RA dependent structure we can measure as shown on the right. Because our scans go at a fixed, between a fixed RA range, so this structure might look like a feature in RA, but it's actually different between left-going scans and right-going scans. So it's not real in the sky. It's something about our telescope. It's scan synchronous. So we just measured this and subtract it out. Also, there is a very common systematic that is temperature to polarization leakage. So a lot of mechanisms could cause this. For instance, a gain mismatch between a detector pair would produce a copy of a temperature into Q and U maps. So in our usual analyses, we measure these scale factors and subtract them out. In Marius, we'll talk about the Bayesian method, where we include all these in the forward model, and the amplitudes are marginalized over. And between both methods, we find consistent results. If we want to measure B mode, we'll also have to deal with T or E leaking into B. We also have other systematics, such as polarized atmosphere pickup from perhaps ice crystals. And we also have some ground pickup we can see. The bottom line is that we do jackknife tests for all of these. So for ground pickup, we do like azimuth tests and so on. So if there's any remaining systematics, they should be way below the uncertainties. So data release. We will release maps and paraspectra for temperature and polarization. We also release catalogs of galaxy clusters and sources. We have no plans to release time order data for now, partly because it's a lot. So SPT-SZ, that's the first generation of SPT experiment. The data is out. SPT poll data release will be released with my upcoming SPT poll EETE paraspectra analysis. And we will also release SPT3G data in the future. And okay, and then we can go to the next part, Marius's talk. How do I leave this sharing?
Yeah, thank you, Jody. So let's get up here real quick. There. So in the next part of the talk, I want to, oh wait, hold on, my screen sharing is paused. Let's try again. There we go. So in this next part of the talk, I want to describe to you some of the efforts that we've done in the South Pole Telescope, and then also in collaboration with BICEP on turning some of this usual analysis pipeline into a little more Bayesian. And as I understand it, I think this is basically kind of a subset of the problem that Cosmoglobe is attempting to do. And so the usual pipeline is actually almost all frequentist, right? It's time order data to maps, frequentist, power spectrum estimates, for example, estimates of the lensing potential, like the quadratic estimate or frequentist. And then we do the very last little bit to parameters as Bayesian. And I think this is totally fine because it's sufficient and it's the simplest, fastest thing to do. But we're kind of entering this territory now where part of this, in particular the lensing estimation, ceases to be sufficient in this framework and actually could be made better if we skip from maps straight to parameters with a Bayesian analysis. And this has been known about this lensing estimate for quite a while. This is almost 20 years ago now. The first papers showed that the noise that you get from the quadratic estimate can actually be orders of magnitude larger than the noise that you would get from a fully optimal analysis, like the bottom curve that you see there. This is for a CMBS4-like experiment. And the reason to understand is pretty simple. The quadratic estimate, it's in the name, it's quadratic in the data. But there's bispectra, trispectra information in the data that informs the lensing, which is just not used by the quadratic estimate. So that's why you can do better. And this paper set up these forecasts, but now almost 20 years later, we're kind of finally at the point where the noise levels are getting close to CMBS4 levels. They're right at where you start to begin to see some difference, but some improvement that can be had. And we're asking, how do we actually do this to real data? So in terms of trying to get more optimal estimates, people have tried a number of things. There's machine learning approaches, which achieve noise levels that are kind of comparable to that forecast I showed, but have challenges in how do you actually extract cosmological information from the reconstructed maps. Maximum a posteriori estimates suffer from this same problem, and I'll describe this a tiny bit more in a second. There's methods like gradient inversion or various little tweaks on the quadratic estimate, which are really nice and will be important in certain limits or in the short term, but aren't really a full solution. And then there's just full Bayesian inference, which is what I have focused on and I'll describe. But just to show you the problem with this cosmological parameter estimation, I want to take the example of these machine learning methods. So this is from those papers. And the idea is super simple. You simply train a neural network to take in input lensed noisy data and spit out maps of the unlensed E modes and of the lensing potential phi. And this paper here also did the patchy reionization optical depth tau, but just focusing on phi and E. And you can do this. It's remarkable that these super simple network architectures give you very good estimates. And the estimates look like the thing that you see here on the right. But so looking at it, for example, here's, from one of these simulations, this is a true map of the reconstructed this is the true kappa map, kappa just being the Laplacian of the lensing potential. And then this is the reconstruction. And certainly, it's tracking the same structures, which is good. But you can see that it's heavily smoothed out. It's like a Wiener filter. Actually, these things basically effectively compute kind of like a nonlinear Wiener filter. But that means that the power is suppressed on scales where the signal to noise is low. And so you can see this in the power spectrum of those reconstructed maps. For example, as you vary the noise of the data, you get a different amount of Wiener filter-like suppression, and you're never actually recovering the theory spectrum of the thing you're trying to reconstruct. So in terms of comparing to theory, this is difficult. You have to debias this somehow. And I think cosmologists tend to think, well, okay, that's easy. I'll just do some simulations and I'll remove the bias. But it's actually a much more subtle and harder problem than this. One way to kind of understand it is that if I do these simulations to debias, I had to have assumed a set of fiducial parameters for my simulations, but those are the exact parameters I'm trying to estimate in the first place. So there's kind of the circularity, which maybe indicates to you there's something wrong with this idea. And ultimately there kind of is, because basically doing this debiasing is kind of the fundamental problem of high dimensional Bayesian hierarchical inference. And if there were easy solutions out there, people would be famous for having developed them. So it is a lot of work to actually do this correctly without losing information. So in the Bayesian lensing approach, which will give us a way to kind of effectively get that debiasing, it's quite straightforward. We simply model the data. And in a simple model here, for example, we say that the data is the lensing operator as a function of the gravitational lensing potential multiplying an unlensed map, which I represent by F, plus some noise. Then you have to specify some priors on these things. For CMB lensing, it's quite simple. The CMB unlensed is a Gaussian random field. The lensing potential unlensed to just the lensing potential to a good approximation is a Gaussian random field. You can approximate your noise as Gaussian. And then there's a hierarchical set of parameters that control these things, theta, that are what we want to estimate. And once you have written all that down, out of Bayesian analysis pops a posterior distribution, which looks something like this. It's actually quite simple, but I'll note it's a very high dimensional function because these F and phi are the actual maps of the unlensed CMB and of the lensing potential. So for something like SPT, this could be hundreds to millions of pixels, for Planck resolution and 10 million. So this is a very high dimensional function. And here I'm just moving it to the top of the slide. But the way to then get constraints out of this analysis is that you have to marginalize over these very high dimensions to get down to the posterior distribution of just the parameters that you're interested in. And by virtue of Bayesian statistics, this is kind of guaranteed to have extracted all of the information, effectively implicitly extracted the bispectrum, the trispectrum, and all of this from the data without you having explicitly constructed it. This is the thing that kind of corresponds to the challenge of debiasing that spectrum, if you want to think of it in an estimator sense. But this marginalization is difficult because this is a million dimensional or more marginalization of a function that's not Gaussian. So this is very hard. Skipping over a bunch of details, I'll just say that the way to do this is or the way we do this for now, at least, is with Hamiltonian Monte Carlo, which is like an MC-MC algorithm that uses gradient information. And I feel like people that have never used it think it's this like really complex thing. And I had always joked that, it's really not. It's like 5 lines of Julia to write it out. And at some point I actually went and put my money where my mouth is and tried to write this out. And one second while I figure out how to make my slides advance. So I did it, and the real thing is 17 lines. So I was a little off, but it's very simple. And this is the actual exact code we use, in this complicated lensing sampler, and it works on CPU and on GPU. And it's actually quite simple. So I would say people don't be scared of doing something like this. In case I imagine the Cosmoglobe members are not necessarily scared of this. So that's basically how our analysis works. And now I want to show you results from having done this to some data from the South Pole Telescope in this recent paper. So here we used a 100 square degree patch that was observed particularly deeply by the South Pole, by the SPT pole instrument. It's the deepest polarization measurements at angular scales that are relevant for lensing. And it's a relatively small patch, but it allows us to test these methods at the noise levels where we expect to see some improvement over the quadratic estimate. So the data model for this analysis, it's a little more complicated than what I had on the previous slide, but it's actually quite nice. We can include in this forward model a number of systematics effects, things like temperature to polarization leakage templates and coefficients like Jody mentioned, beams and transfer functions, global polarization rotation calibrations of the instrument. And all of these things can have free parameters, which are then marginalized over in the analysis, letting us, constrain and reduce the impact of systematics. So the output from something like this is, one second. The output from something like this is the set of samples of the maps given the observed data. So here are the set of samples of the unlensed E modes from the analysis. I'm not sure if you can see in the video, but it's actually kind of like warping because this is the unlensed E modes, and the lensing potential by which they're being delensed is itself an uncertain quantity that's varying. And this kind of summarizes the information that you have a posteriori on what the unlensed E modes are. You can similarly plot the samples of the lensing potential phi. It looks like this, this is essentially the deepest map, kind of map like this made from polarization, but you can still almost, it almost just looks like noise, right? You can sort of see some structures in there. But this is going to be something that by the time we get down to CMB S4 like noise levels is going to be really massively improved. Here's just taking the exact same data set and just in a simulation reducing the noise down to S4 noise levels, and you can see sort of how much better just visually this reconstruction will be. Now a little more quantitatively, we have along with those samples of the maps, there's samples of the parameters that we varied, in particular those systematics parameters that I mentioned. And a really nice thing is that these are now just jointly estimated along with everything else in a totally self-consistent manner. In previous analyses, the systematics uncertainty exploration was kind of this other thing that was tacked on at the end. And then this isn't just sort of a cosmetic thing, but it actually leads to some real improvements in the impact of these uncertainties. For example, the impact from the polarization calibration uncertainty on previous SPT lensing analyses was actually getting to be quite significant, almost half a sigma on the amplitude of lensing. And the reason for that is because, well, it had not been that important previously, and the analysis dealt with it in a way that was kind of suboptimal. But you could do something like a bias hardened estimator, which would have been better. It could have been done. But in the Bayesian framework, you just get that for free. And we reduced the impact of this uncertainty from half a sigma down to almost 0. And ultimately, we did find about a 20% improvement over the quadratic estimate, which was one of the main goals of the work. One of the things I thought was the coolest was that actually our ability to then take this and estimate parameters jointly, parameters that control both the lensing potential and the unlensed E modes. Here we're showing constraints on the amplitude of the potential, a phi, and a contribution of a lensing-like signal, but Gaussian, to the unlensed E mode, sometimes called AL. Here sort of 1 minus that plotted, delta AL. And this is the kind of thing which is actually quite difficult and has not, I believe, has not been done to date because it requires this complicated covariance calculation between the reconstruction and then the delensed data. And that's something else that pops out of this sort of for free. So in the last couple of minutes, I want to talk about our extensions to this analysis that we've been doing under the working under the South Pole Observatory, which is the combination of forces from SPT3G and BICEP Keck, with the goal to estimate the tensor to scalar ratio to put the best constraints on it that we have. And within this collaboration, there's sort of 3 pipelines, which are creatively named A, B1, and B2. The one that I'm working on is this B2, which aims to do full Bayesian inference from these 2 instruments. There's a number of other people that contribute here, some of who are on this call. And the goal from from this analysis is, of course, to estimate R. We think that we can get to, with data by the end of 2024, down to about 3 × 10⁻³ uncertainty if R were 0. And you can see from this plot that there's actually a big difference between whether we don't attempt to delens the BICEP data or whether we delens it. So this really begins to be limited by this lensing signal. And if you can estimate the lensing better, you can remove it better. And so these Bayesian methods can actually improve constraints here. So here, quantitatively, what can they do? So for this is a forecast for using SPT3G, the full survey to reconstruct the lensing potential. And you can see on the left panel, the effective noise in the quadratic estimator spectrum is actually going to be almost a factor of 2 lower with the Bayesian method compared to the quadratic estimate. And that will in turn correspond to reducing the residual lensing after delensing by about a factor of 1.3. So these are significant improvements we want to make, which were in fact built into the plot that you see that I just showed on the previous slide. The way to do this is straightforward. We sort of just extend that posterior distribution. We extend the data vector to include the BICEP data, and then we have to model additional things that are relevant for the BICEP data. So the part that we've already done is the 100D deep field. That was the SPT results I showed you. We want to add the tensor to scalar ratio. We need maps of galactic dust and synchrotron, which are now jointly estimated, and then the parameters that may control those models. And similarly, you can still get this posterior distribution, which is a little more complicated now, but it's very doable. I want to highlight that one of the things that enters here is this observing matrix that you heard about at the beginning of today. And this is a really, really useful data product for these Bayesian analyses because it just gives you a way to map, the true sky onto the observed quantities in a really straightforward way. And I also want to highlight that this is somewhere where doing this on GPU gives just massive speed ups. So multiplying this matrix by a vector is about 2 seconds on CPU, or about 5 milliseconds on the GPUs that we're running. So it's fair to say that the fact that you can do this takes this analysis from not possible at all to actually fairly easy for the BICEP part. We can explore things like the dust models that we put into the BICEP analysis. This is just a small example where we were looking at comparing a Gaussian dust model, which is what previous BICEP analyses have done, with one developed by Andrei Frolov, which basically says that the thing that's Gaussian aren't the E and B maps, but rather the polarization fractions. And then the Planck temperature sky gives us a fixed thing to calibrate that to. And I'm showing you here samples from a chain, from a BICEP only chain, a forecast run where we use one of these 2 different models, and then put in as the truth this non-Gaussian model. And I think to the astute eye, you'll see that the top one, you see some visual difference in the distribution of these samples, which are sort of characterizing, given this model, which may be non-Gaussian or not, and the data, how do we reconstruct this dust? And the good thing is that mostly for in terms of the resulting R constraints, there's actually not that much difference between these 2. So, this is some particular simulation with parameters. So this is not an overarching statement yet, but, at these noise levels, for this, we certainly don't see much difference in the resulting R constraint. And so that's a good sign. We are also working on including the full SPT3G data set in conjunction with this and including the lensing, like I was mentioning. This is actually a much harder problem because 3G has so many more pixels. So the biggest patches of sky we can really do this on are about 100 square degrees for now. And we can still run these chains. We can get constraints on foreground parameters and lensing parameters that recover the input truths. But the correlation lengths can be quite large, in essentially the thousands, like you see on the right plot there. So this, I think, is a big challenge, and this is one of the main things that we're working on to scale this up to the full 1,500 square degrees. But I think we can get there. So this is my last sort of 2 slides of a little bit of text. In the spirit of this conference, I wanted to just summarize what I think the challenges and advantages are of this method. The challenges, I think, are that we need fast map level differentiable forward models for the data for things like the dust, instrumental effects. Sometimes people just have models of the power spectrum, but since we're trying to extract info on lensing from all of the different higher order spectra, we need to model the foregrounds of those higher order spectra. They're of course computationally intensive, but there's big advantages. You get the optimal answer for free, no further thought required. You can explore the impact of non-Gaussian assumptions about foregrounds. You can combine experiments, obviously, and actually modern automatic differentiation makes a lot of this coding a lot easier than you'd think. And also in the spirit of collaboration, I thought, what can we offer and what could our group benefit from? What we can offer, the code that does this is this Julia code called cmbLensing.jl, which is built on Julia GPU's automatic differentiation. The choice of Julia is really because of the ability to easily leverage that GPU automatic differentiation to do this sampling and coding. It's a very mature library, which I would encourage anyone that wants to do something like this. And it does sound like this is a subset of what Cosmoglobe wants to check it out. So we already have a data product that could be offered, which are these posterior samples from the SPT analysis. And in terms of what our group could benefit from, I think more people working on developing these map level differentiable forward models for things like point sources, SZ, galaxy, machine learning could be used here. That sort of seems like a necessity. Temperature is somewhat unexplored for us. Our main focus has been polarization. And from this talk, it may seem like Bayesian is the same as sampling, but I would actually stress that that's not the case. There's a lot of different ways to explore this posterior, things like variational inference, likelihood-free inference, expectation maximization. I'm working on another alternative. And all of these have the potential to be faster and I think should be explored. And then the final thing to highlight, which I really think we will need to scale anything like this up to the full sky, is just GPU spherical harmonic transforms, which I'm kind of surprised don't exist yet. But if someone were to do this, maybe they're on this call. I'm not sure. Anyway, that's all I had. Sorry for going a little over, and take any questions.